The Challenger Center for Space Science Education presents Marsville, the Cosmic Village. An interactive teleconference to help you prepare for the adventures of exploring and discovery. Corporate funding for this program was provided by Rockwell International Corporation. And now, from the studios of WQED-TV, your host, Dave Zarin.
Thanks, everybody. Thank you. I'd like to welcome you to this special interactive exploring event. There are over 1 million of you watching all across North America right now. My name's Dave Zarin, and I'll be your guide for the next hour. We've got an exciting program ahead of us. Together, all of us are going to explore the challenges of building and maintaining a human settlement on Mars. Not only that, it's going to be up to us to rescue this settlement from a powerful dust storm that threatens. Well, how are we going to do it? We're going to start out by discovering some of the important facts on Mars, facts that scientists have learned over the centuries about this mysterious planet. Then we'll demonstrate some simulations, activities you can do right in your own classroom. They're designed to help you discover and learn by trying things out. And they'll prepare you to solve the challenges you yourself may someday face on Mars. That's right, you, because your generation may be the one that takes that first bold adventure to our planetary neighbor. Now, you're probably wondering about these giant plastic bubbles you see in back of me. Well, they're actually called Mars habitats, and those are the places that astronauts will someday live in when they get to Mars. But instead of me telling you about it, why don't we go have a sneak preview? Come on along. You know, when we get to Mars, there are going to be some places up there where we won't want to live because of the terrain, and we're going to have to put up things that look like this. Giant tennis bubbles, kind of greenhouses, where people can get inside and, well, the doors open up. You can see that we have a flap here. You can get inside the house, and they're kept inflated by giant fans. We're going to have an energy supply when we get to Mars, and you can see that they're blown up, and they're going to provide the safety and the comfort that human beings are going to need when they get to that angry red planet. We're going to tell you lots more about these habitats a little bit later, but first of all, I want you to meet some of the young people that are going to help us this afternoon learn about Mars and go through some Marsville activities. We have students from Boyce and Fort Couch Middle Schools right here in the Pittsburgh area. And this team of young people, all 7 of them, have done the activities we're going to show you today. They'll be helping me guide you all through this afternoon's teleconference. Let's meet them. First of all, joining me is Ariel Paredes. Come on up, Ariel. Let's give her a hand. Nice to have you here. And next we have Niraj Chandra. Niraj. Good move. All right. Next we have Scott Davison. Come on up, Scott. Our next team member, Lauren Purnell. Joining us next is Ellie Henderson. Our next team member is Rob Solenday. Come on up, Rob. And our last team member is certainly not least, Elise Nam. Elise, come on up. All right, that's our team. Good-looking group. Now that you've met everybody, it's time to begin. You know, one thing we've learned about exploring is that it helps to follow certain steps. Let's talk about them. What are these steps that we're going to tell everybody all across America about today? Elise?
Challenger Way.
The Challenger Way. And how many of these Challenger Way steps are there? Rob?
4.
There are 4 of these steps. Well, now with some help from our studio audience, we're going to share these 4 steps with you. Let's find out what those steps are. And there we have some people in our audience. Let's all of us together. What's the first one?
Get the facts.
And after we get the facts, what do?
Work together.
All right, and number 3, after we work together, we
Work it out.
And the last thing we do is
Consider the consequences.
All right, thanks a lot. Good group. Those are our 4 steps, and it's important that we understand each and every one. So let's begin our adventure by getting the facts. The first human expedition to Mars will probably look something like this. Look closely at these Mars explorers. By the time the mission to Mars is launched, you may be about this age. Your generation could be the one making the trip. Your footprint, the first one on the planet. But you don't have to go to Mars to be an explorer. In fact, all of you at some point in your lives are going to be explorers. You may end up walking across the surface of a distant world in space, or you may uncover the mysteries of the ocean floor right here on Earth. Maybe you'll discover a cure for AIDS or cancer, or analyze the inner workings of the stock market. What you're learning in school right now will make those adventures possible. Scientists have been working to get the facts about Mars for hundreds of years. Throughout the 1600s and 1700s, astronomers used telescopes to record detailed observations and sketches of Mars. Then, with the dawning of the space age, we were able to send robotic spacecraft to orbit and land on Mars. They took pictures and gathered samples, giving us the kind of facts needed to survive on the planet. The pictures from the probes revealed a harsh landscape without any visible water and no signs of life. There are a lot of similarities between Mars and Earth. Like Earth, Mars has an atmosphere, polar ice caps, seasonal changes, and volcanoes. But Mars is also very different. Its atmosphere is much thinner than ours. Its volcanoes much bigger, making our tallest mountains seem like mere hills. On Mars, the tallest volcano, Olympus Mons, towers 27 kilometers, 3 times taller than Mount Everest, making it one of the largest volcanoes in the solar system. As you can see, Mars is a rocky, desolate world. No water exists on the surface in liquid form, making it drier than the driest desert on Earth. Mars does have an atmosphere, but is much thinner than Earth's. The predominant gas is carbon dioxide, making up 95% of the air, and there's very little protection from ultraviolet rays. No conclusive evidence of life on Mars has ever been found. Many people have wondered why Mars is red. The planet's oxygen has combined with iron in the soil and the rocks, much like oxygen and iron combine on Earth to form rust. Much of the footage you just saw was used in the television series Space Age, which is airing Monday nights on public broadcasting. It's also an excellent way to get the facts about the space age. We're going to explore a few more facts about Mars now, and so we need some of our team members here to represent celestial bodies. 3 of them represent the Sun. We have Niraj as the Earth and Elise as the planet Mars. Now, to get some idea of what conditions are like on Mars and on Earth, we need to get some things that you can do in the classroom. And first of all, let's find out what the distances are of these planets from the Sun. Let's get some ribbons to help us illustrate that. We've got a green ribbon. You can choose any color you want. And it graphically illustrates for your class how far these places are apart. And Niraj, as Earth, why don't you turn that card around and tell us how far you are from the Sun?
I'm about 150 million kilometers away from the Sun.
Okay, and that's an average. The range is from 147 to 152 million kilometers, depending on the time of year. Now, Elise, representing Mars, is even farther out in the solar system. Let's find out how far away she really is. Get a different color ribbon, have some contrast. We've got a red one, and we will stretch this behind Earth all the way out to the red planet. And Elise, why don't you turn that around and tell us how far you are from the Sun?
About 250 million kilometers from the Sun.
Very good. And again, that's an average. The range is 207 to 249 million kilometers, again, depending on the time of year. Now, the distance away from the Sun is important because it's going to affect temperature. We're a long way from the warming rays of the Sun. How warm and how cold does it get on Earth and on Mars? Well, to illustrate that, we have a couple giant thermometers. If you celestial bodies want to put your ribbons down, we'll bring the thermometers up here. And as we pass them along, I'm going to ask Lauren which one she thinks is going to be colder. Give us your hypothesis, Lauren.
Probably Mars.
Probably Mars. Why do you think so?
Because it's farther from the Sun.
All right, that's a good guess. Let's see if she's right. Let's check out these 2 thermometers and ask Mr. Earth here, how warm do you get?
I get up to about 58 degrees Celsius.
All right, and that's about 130 degrees above zero. And where on Earth would you find places like that?
In the desert and in places like Death Valley.
Very good. And you can see the temperature can drop as low as minus 88 degrees Celsius, which is about 130 degrees below zero. And where on Earth would it get that cold?
In the Arctic and the Antarctic.
Very good. All right, now let's compare that to the temperatures on Mars. Elise, how warm do you get?
About 22 degrees Celsius.
All right, if we convert that, that's only about 70 degrees Fahrenheit, which is about room temperature, so it's not all that toasty. But this is the more important figure. Tell us how cold it gets on Mars.
About minus 125 degrees Celsius.
All right, and that is well beyond the tolerances of life. If we go to Mars, when we go to Mars, we're going to have to take pains to adapt ourselves to temperatures that are that cold. Something else you've got to consider. The sizes of the planets are different. In fact, the size of the Sun compared to the size of the Earth is about 110 times larger. And if we compared Elise, Mars to Earth, would find it would be about half the size, even less compared to the Sun. Now, what about size? How does that affect life on the planet? And I'm going to ask Ariel if she has any idea.
Well, gravity.
Gravity would be different. Which of the two planets do you think has the stronger gravity?
Earth.
Earth. All right, well, let's find out if she's right. And to illustrate that, this is again something you can do in your classroom, we're going to have Allie come up, and she's got a scale in her hands. Let's bring her onto the surface of Earth. And Niraj, don't mind us. Allie, why don't you step on there and tell everybody how much you weigh?
65 pounds.
65 pounds. All right, she is quite a lightweight. Let's find out if she is heavier or lighter on the surface of Mars. Let's move your scale over to Elise's place here. We'll have you stand on there, and let's check your weight.
25 pounds.
All right, now that is less, and why do you think it's less?
Because there's less gravity.
All right, so our original thought was right. Ariel was right. There is less gravity. It's 38% of the gravity on Earth, so it would be a lot easier to move around on the surface of Mars. Thank you, Ariel. Well, we're going to be moving on now to the next step in the Challenger way. And to find out what that is, now that we have the facts, what are we going to do? Scott, why don't you help us out?
Work together.
We are going to work together. We have been working together all along, but now we're going to change our focus. We're going to go to something called a simulation.
All kinds of simulations can help you get ready to explore Mars. Astronauts do simulations all the time. These Russian cosmonauts are floating in a pool to simulate the effects of weightlessness on a long journey into space.
На подголовник. Немножко, чуть-чуть. Ну, смотри, если тебе так тяжело. Внимание! Хоп!
It is known that being weightless for a long time causes changes in bone and muscle tissue. And since a journey to Mars and back might take years, we need to know more about the effects of low gravity on the human body.
Смотреть противовращение.
Isolation team is determining that they're...
But you don't have to be an astronaut to take part in simulations. These are students just like you, and they're flying a simulated space mission. They're aboard a simulator called a Challenger Learning Center, created by the Challenger Center, experts in educational simulation. At pre-mission briefings in their classrooms, they train to perform the roles needed on actual space missions. Then they come to the Learning Center, a full-scale simulated spacecraft and mission control. The journey is about to begin. One student might start out as the mission navigator. Another monitors life support. Someone else simulates communication with colleagues back at mission control. It is a team effort as students perform scientific experiments, deal with emergencies, and tend to the routine problems that are bound to occur. Everyone cooperates to make the mission a success. Here's another type of simulation. It's called Marsville. To build it, students, just like you, must first research the demands of living on Mars. Then they build life support systems and design inflatable habitats based on preset specifications. It takes everyone pitching in with their own ideas to make the thing work. That's the goal of simulation, to work together, to try out new ideas before the real thing happens.
When students are working on Marsville, they have to consider some very real problems. Think about it. We've already learned that there are big differences between Earth and Mars. And that raises some questions, like how will these differences between Earth and Mars affect you as an explorer? Could you, for instance, just step outside your spacecraft and go right to work? Rob, what do you think about that?
I think you can, Dave, because you need oxygen to breathe. Without oxygen, you would die.
Absolutely right. You couldn't just step right outside. And as Rob just told us, you'd have to build some kind of life support system. In fact, on the Marsville project, students build models of 8 different support systems. Let's see if we can figure out what those systems are. I've got 8 cards here. Each one has some symbols on, and let's see if we can identify the 8 things we'd need to survive on the surface of Mars. All right, here comes the first one. What do you think? Water. We need some water on Mars because it's all tied up in ice caps right now. What about
Weather
this?
station.
Weather station.
Temperature control.
Temperature control, because it gets very what on Mars?
Cold.
Very, very cold. So we've got to regulate it so we can survive. Now this one is tough. Look at this ornery looking guy here. What do you think?
Garbage.
Coffee?
Toxic
Do we need
waste.
coffee on Mars? Huh?
Garbage.
Garbage maybe?
Waste management.
Waste management? Food? Food is a good idea. So this could be coffee because we've got to drink and we've also got to do what? Eat. All right, so we need to take some nourishment with us when we get up there. There's no supermarket to run to. What about this one with these posts on, these signs?
Navigation.
Navigation, you guys are good. Yeah, because when we get up there, there are no maps we can buy at the local service station. And we have to find out not only how to get around, we've got to build vehicles to get us there. Now this looks like something for a birthday party. Couple Mylar balloons. Air supply. What's the air like on Mars?
Carbon dioxide.
And what do we breathe? So we got to take our own. You guys are great. How about this one?
Recycling.
Yeah. Do you folks recycle at home?
Yeah.
Good. You're going to do it up on Mars too. Waste control. This is an interesting one. Look at this guy.
Communication.
Yeah, we've got to find some way to communicate with other bases up there on Mars because sometimes it might be critical to get in touch with them. And last but not least, now look at this one. Looks like a Ghostbuster sign. What is it?
Recreation.
Now, how'd you get recreation out of this?
Like no work.
It says no work. All work and no play makes for a real dull astronaut, so you've got to enjoy yourself while you're up there. Let's have a look now at some of these 8 systems as they were designed by teams of Marsville students.
This is where the raw sewage comes into our waste treatment plant. It goes into the pulverizer oxygenator bacterial digester, which adds oxygen to the sludge to promote the growth of aerobic bacteria instead of anaerobic bacteria. You see, anaerobic bacteria produces methane gas, and if there is that in our system might explode. Sludge is then pumped to the centrifuge. It spins around to create artificial gravity because there is only 1/3 of Earth's gravity on Mars.
The sludge is then sent over to the screen filter press, where more water is removed, again sent to storage tanks, and then sent to hydroponics.
Hi, my name is Chad, and I will be explaining the Marsville water supply. Our team has devised this system. It consists of a chopper, a melting station, 2 water treatment plants, and storage tanks, and a recycling plant. The way our system works is that ice is chopped from the northern polar cap, comes through insulated piping to the melting station. The melting station runs by solar power and by the temperature of a Martian day.
Mars fact number 2 is the temperature. Mars temperature can go up to 160 degrees and can go down to 220 degrees below zero. This allows us to have a melting station. Mars fact number 3 is 38% of Earth's gravity. Knowing this, we have to tie down or lock down the pipes, as you see here, 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 and here.
Hi, I'm Ralph, and I'm here to explain the Marsville air system that our team has devised. It consists of a main system and a backup system. Our main system consists of plants, grow lights, and sprinklers with a CO2 or carbon dioxide pipe in from outside Marsville. The plants use the carbon dioxide to produce food and oxygen. Oxygen is released and is piped out through air filters, which you see here, through insulated pipes.
This is the base of our system and controls everything. Here's the stem of the satellite, which has the wires going up here to produce waves to go over the rough terrain on Mars. This is the satellite, which does what I said. This is the on and off switch so that we can turn it on and off.
Well, that looked like a lot of fun. Yeah, all right. Well, now I want you to imagine this. Imagine that these systems have been set up and they're all working perfectly at a human settlement on Mars, a base on the planet's surface. This settlement is doing well, but its continued survival depends on critical resupply missions, missions that bring in food and medical supplies and spare parts. But there's a big problem, a violent and destructive dust storm. Roaring winds could very well doom the base if supplies don't make it through. These storms can engulf the entire planet. And the question is, what causes them? Well, one factor appears to be the polar ice caps. When they recede during the Martian summer, we believe they release carbon dioxide. This thickens the atmosphere and creates a greenhouse effect, causing the atmosphere to heat up. The heat in turn leads to higher winds. Right now, one of these enormous dust storms has surrounded Marsville. Given these high winds, our challenge is to design a resupply payload that will reach the settlement safely. Now, does anyone remember what our next exploring step is? Who knows? Elise.
Work it out.
Work it out, that's right. We need to work it out. We need to design a payload that will go where we want it to and not crash into the settlement. Now, those of you who are pre-registered for today's teleconference should have received an activity packet like I have here. It's called Rescue on Mars. Briefly, let me tell you what happens. Students should simulate the problem by using common materials to build a Mars village and then design trial payloads to make it through high winds. A fan is used to generate the wind. Let's take a closer look.
These student teams are solving the Rescue on Mars challenge in Washington, D.C. Here's what you need to do to complete the same activity. There are 3 steps. First, you need to build a model of the Marsville settlement. Size guidelines and other facts are provided in the activity packet. Your job is to work with others to answer critical questions and to make important choices. You'll have to decide what the structures will look like, what they'll be made of, where they'll be placed. You'll have to plan the layout of the entire village, building everything, and then putting it all together.
This is supposed to be in Marsville, and they're working. It's like a town, and we're working, and they're building a payload, and they drop it over the fan, and it's supposed to land without hitting our town.
For step 2, you'll need to build and test different payloads. The payloads must meet certain weight restrictions, and since you have to drop them from a certain height so that they land close to the village, wind is a critical variable. A fan blows to simulate the wind on Mars. And since you don't want the payload to land too close to the village, the team needs to build several different designs and test each one of them with the fan. Step 3 is actually dropping the payloads onto Marsville. In simulations, as in real life, things don't always go perfectly or according to plan. Exploring, then, is a constant process of trying things out, experimenting, testing, and then trying them again. There isn't just one right way to do things, and failures can help you to understand things just as well as successes.
Now let's look at teams of students at the Science Center of Iowa, the site of the Challenger Learning Center in Des Moines, as they work out this challenge. Those were some pretty interesting solutions to getting a payload onto the Marsville site without crashing into it. Good engineering skills. But it looks like you guys have some equally good suggestions about how to get this done. Let's find out from our team members how to get a payload onto Marsville and not wreck everything in the process. Let's start with Niraj here. Why don't you tell everybody about what you've got?
Well, I made like a delta wing type of thing, and to add weight, I put some paper clips on, and I think mine worked pretty consistent, and my only problem was my wingspan wasn't big enough So sometimes it steered off course or something, or it fall short.
Well, it looks like if yours was the prototype, the final product is what Rob has over there. Rob, you've got a bigger wingspan. Did that help?
Yeah, it helped a lot. First, though, it was going too far over, so I had to chop the back of it off. Then I had to angle the nose down like this to get it on target.
How many times did you have to build that until you got it right?
This was the original one that I built. The nose is pretty smashed up on it.
Yeah. Well, it should look like that if you tested it out. All right, let's look at some other solutions here. This looks like some kind of propulsion system. Ariel, what's that? What are those balloons for?
Well, I wanted to have air, and so when I let go and stopped blowing on it, it would just flow and go into the square part, but it didn't work because it was too heavy and it didn't have enough propulsion, and that's where Scott got his idea.
Oh, so this is the action-reaction, Isaac Newton's law. All right, well, yours is the new and improved version. What is it, Scott?
Mine works better since it has the fins to help guide it and a longer...
All right, so you were more accurate with the fins.
Yeah.
All right, and the other three of you look like you've got some parachutes here. Well, who wants to tell me about parachutes?
I will.
Lauren, tell me.
Well, the problem with parachutes is once they did catch the wind, which sometimes they didn't, and they just go straight down, they'd drag on and they wouldn't stop at the landing site. So we had no control over them. Mine, I put some straws in to keep a form, so hopefully it would catch better. But as I said, it was a problem because it would drag on.
All right, so the big wingspan seemed to be the best and the parachutes were the worst. You know, those of you watching probably came up with many other payload ideas. If you'd like to share some of those solutions or ask a question of one of our experts here, now's the time to get on the phone and use that 800 number provided in the registration packet. And don't worry, even though you didn't pre-register, we'll give all of you a chance to call in just a moment. Now let's see how your payloads actually worked. Allie, take it away.
That's me. When I attached a balloon to a cup, but it didn't work because it had nothing to carry and nothing to keep it up in the air.
All right, Scott, what about you?
I was testing my propulsion idea, but it kind of landed in the area, but it didn't.
All right, astronaut Niraj, how about your system?
Well, my system, I think, worked pretty well. It landed in the square most of the time, but as you can see, it wobbled a little bit because of the test damage.
All right, first mate Elise, you used a parachute. What happened with it?
Well, it didn't really work too good because it was kind of heavy, and it kept on dragging when it got to the floor.
That wasn't too bad. And Lauren, there you are. Tell us what's going on.
So this is my attempt at the wide length airplane. It didn't quite work. It just fell.
Okay, and Rob, you told us earlier you had one of the best ones. Tell us what happens here.
I made a big paper airplane, and at first it didn't work, so I had to cut off part of it. But after that, it worked very fine.
All right, and there you are up there right now with your big wide wing. Here it comes, in for a perfect landing. Wonderful. And we have one more shot of Allie. Here's our final attempt. You guys were great. You know, as we've just seen, there can be many ways to solve the same problem. And that brings us to our fourth and final step in exploration, which is...
Consider the consequences.
All right, that's right. Consider the consequences. Well, what we have in front of us now is a model of the Mars village that our team up here put together. Now, when you all put these different buildings onto Marsville, what guided you? What determined what went where?
Well, we thought about what do the humans need to survive, and we put that into priority. First, we need the habitat, because that's where we live. Second, we need air supply. Thirdly, we need water supply. And last, we need the greenhouse for our food.
Okay, well, the greenhouse is up here on the front. This cup represents what, Lauren?
That's the water supply.
The water supply. This is your
habitat.
Habitat, and the two balloons, what do they represent?
Ariel designed this. Let her answer that
Ariel?
Well,
one.
this is the air supply, and in the bigger balloon, it's the oxygen, and the smaller one, it's carbon dioxide. And there's a pipe, an underground pipe connecting the greenhouse to the oxygen, the air supply, and the carbon dioxide is sent to the greenhouse while the oxygen is being recycled from the greenhouse.
Very good. So that's photosynthesis in action, helping us survive on Mars. That's good. Now, this in the front here, Rob, I know you built this. Why don't you tell me what that is?
Well, it's a weather station, and the big antenna is for taking weather meters, and on the side of it there's a weather balloon with a little package of controls, and then there's the four straws. They're like lights, so you can see what you're
And
doing.
this is what right here?
That's like a transmitter antenna, and it's also backup in case the communications goes out.
Very good. Okay, so you were thinking ahead there. And what's this right here? This is some kind of solar collector? Who built this?
Me. That's the communications tower for communicating to and from Earth.
All right, well, that's terrific. You guys, you amaze me all the time what you can put together. You know, not only did you find solutions to the problem, but you looked at those solutions and how they might affect others. That's very important for problem solving and decision making. Let's have a round of applause, everybody, for all these great problem solvers and explorers. You know, Mars continues to lie ahead of us in the future, in our future space explorations. But right now, we'd like to continue today's exploration with individuals who have already been on space missions. They have experience in the space frontier. Joining us in the studio is a former NASA astronaut, General James McDivitt. He was the commander of the Gemini 4 and the Apollo 9 missions, and he was in the Air Force. He is retired now as a brigadier general. And he is currently serving as a senior vice president for Rockwell International Corporation. Join me now, and please welcome General Jim McDivitt. General. Thanks for joining us this afternoon.
Thank you. Pleased to be here.
Good. We are pleased to have another space explorer joining us today via satellite from Chicago. Just weeks ago, Dr. Mae Jemison flew her first space mission aboard the Space Shuttle. Dr. Jemison has a background in both engineering and medical research with a doctorate degree in medicine. Dr. Jemison, thank you for joining us today.
Oh, it's wonderful that I could be here with you.
We have some questions for you just a little bit later. And we also have another special guest who is ready to answer specific questions that you might have about a journey to Mars. Dr. Michael Griffin, joining us from Washington, D.C., is NASA's Associate Administrator for Exploration. In this position, he is responsible for planning and executing the exploration of Mars and the Moon. Dr. Griffin, thank you for joining us this afternoon.
Well, thank you very much for inviting me. It's a pleasure to be here.
Very good. As we said earlier, our student team of explorers will be on hand up here to take your calls about the Rescue to Mars activity that you've just seen. So now's the time to call in a question for any of our distinguished guests at the following number: 1-800-MARS-321. One more time, that's 1-800-MARS-321. General McDivitt, why don't you take my place on the stump here, and I'll move out into the audience. And we have a question out here for some members of our audience, for our team. And who was the young man who was going to ask that? All right, why don't you stand up for us and tell us first of all where you're from.
I'm from Fairview Elementary at Fox Chapel.
And that's right here in Pittsburgh, isn't it?
Yeah.
All right, and your question goes to our Marsville team, our 7 students. What's your question?
We built our own Marsville, and we had to figure out the area and volume for math class. And I wondered if you used the same way.
Okay, that's a good question. Who up there wants to respond?
Well, I think you should ask Robbie, because he's the one that designed it.
Well, actually what I did, I took the square paper and I measured it to the dimensions, the minimum, because I didn't want a really big thing. And then I took the cup. It doesn't cover as much space, but the piece of paper is there holding its position. Then I put the straws around it for light poles to put on the outer markers of it.
Okay, very good. Anybody else have anything to add to that?
All of them here have been measured properly, and they all meet the dimensions required.
Okay, thanks very much for your question. Now, we also have a question for General McDivitt from Rashid Marshall. Rashid, could you identify yourself here in the audience? Let me go on over there. Rashid, why don't you stand up for us? And could you tell us, first of all, where you're from?
Prospect Middle School in Mount Washington.
And that's also here in Pittsburgh, is that right?
Yeah.
And you have a question for the General. What is it?
How does it feel to be in zero gravity?
Well, Rashid, that's the nicest part of the whole trip. You can float around and just have a great time. The trouble is you want to make sure that you don't get stuck out in the middle. You can imagine being stuck in the middle of this room where you couldn't get to the floor or the ceiling. But generally when you push off, you just float very gently to the next wall, bounce off and come back again. It's great. Got to try it.
Okay, very good. We have a questioner via telephone. Thanks for joining us today. Welcome to the Marsville teleconference. Could you tell us where you're from?
I'm from Anaheim, California, and I go to Estrella Walter School. My name is Matthew Ragland, and my question is, how do you think exploring Mars will help human beings?
Matthew, who would you like to answer that question? We have General McDivitt here. We have Dr. Jemison in Chicago, Dr. Griffin in Washington. You have a lot of choices, or you can ask the question of our youngsters on camera.
I think the General McDivitt.
General. And could you repeat your question one more time?
How do you think exploring Mars will help human beings?
General.
Well, that's not something we can answer in the next hour, but I'll try it in 30 seconds. When we went off to the moon during the Apollo program, we really weren't sure what we'd find there. And as a result of that, we got a better insight into what the history of our own Earth is. We've had a better idea of how to operate in space. I think when we go to Mars, we're going to be stepping further out into the universe. The moon was pretty close to Earth. It's only about 250,000 miles away, where Mars is a long way away. It really will be just the first stepping stone for us to go out into our own universe. So I think from that we're going to get a lot of insight into our universe, the one that we know today in our galaxy, and then back to our own planet.
Okay. Thank you, General. Thank you for your question. We have a question for Dr. Griffin in Washington from Brian Nolan here in our studios. Brian, where are you? Let's go on over and talk to Brian. Brian, would you stand up for us? And would you tell us where you're from?
Woodland Hills East Junior High.
Here in Pittsburgh.
Yeah.
And your question is for Dr. Griffin in Washington. What is it?
Would the trip to Mars be strictly with the U.S. or would it be an international project?
Very good. Dr. Griffin, did you hear the question?
I sure did. And I would say that at this time we don't know whether the trip to Mars will be strictly a U.S. affair or an international venture. But I can say that I strongly believe and hope that it will be international in scope. I think that by the time we are ready to venture to Mars, there will be a number of nations, not just the United States and Russia, which are capable of participating physically, and I would hope that even those nations whose space technology does not allow them to directly participate would also join in the mission in whatever capacity they could help.
Dr. Griffin, thank you. Brian, thank you for your question. We have a call coming in via phone. Go ahead, please. Could you tell us where you're from and who you'd like to ask a question of?
Hello, this is Kevin, and I'm from Maryland, and I would like to ask a question to Dr. Jemison.
Yes, go ahead.
How heavy do you feel when you enter into the atmosphere?
Could you ask your question one more time?
How heavy do you feel when you enter into the atmosphere?
Dr. Griffin, how heavy do you feel when you enter into the atmosphere?
Well, Kevin, I think one of the things that you really find out is that initially when you're up in space, you feel very light and you're floating, and as gradually as you come down, you start to feel a little bit heavier. And things that you ordinarily pick up very easily feel very, very heavy. For instance, if you pick up a roll of tape, all of a sudden it's extremely heavy. And standing up, you feel like, oh gosh, I must have gained 200 pounds while I was up. But gradually that all goes away and you're able to get your muscle strength back. One of the things that's going to be interesting is what happens when people stay up for longer periods of time, because right now, on the shuttle program, we stay up for 7 days, maybe one flight stayed up for about 2 weeks. But people who stay up for extended periods of time, months at a time, or longer, then they may have more problems readjusting because they may have lost more of their muscle strength. So you feel a lot heavier, but right now for 7 days you can get up and walk around. As we stay up longer, we're going to have to try to figure out how to exercise to keep all our body strength up.
Dr. Jemison, don't go away. We have another question for you from our studio audience. Natasha Martinez. Natasha, if you could just stand up, please. Dr. Jemison's waiting for your question.
Yes, I would like to know what college courses would you suggest for an African-American female to take that's interested in space?
I think really you take the same courses anyone else takes. People are interested in space. You have to decide what it is you want to do. Space exploration has all kinds of people involved, not just the astronauts that you see. And then there are all kinds of astronauts. We have people who have degrees in medicine and chemical engineering, in mathematics, people who major in geology or geography, astronomy, physics. So basically the thing to do is to take the classes or to major in something that you're interested in, that you know that you want to do. So if you're interested in biology, take biology classes. If you're interested in physics, take physics classes. The main thing you have to do is to remember to believe in yourself and to go over the hurdles that sometimes may come in front of you and understand that your dream can really become a reality.
Dr. Jemison, thank you. That's great advice there. You know, before we take the next question and before some of our viewers have to leave us, we want to let you know that this teleconference is just one of Challenger Center's many educational programs. We've been showing you the activity called Marsville, the Cosmic Village, something all of you can get involved in. If you're interested in running Marsville for your classroom, the Challenger Center has available for purchase a Marsville resource package that includes the following. We have some young men here in our studio that are going to show you what you can get if you write in. You can get a curriculum packet. We also have a VHS cassette called the Marsville Resource Video, and also a poster called An Explorer's Guide to Mars. Guys, if you could hold all those up so people can see them. Terrific. Okay. You know, for information on ordering, you can write to Challenger Center at the following address: 1055 North Fairfax Street, Suite 100 in Alexandria, Virginia, 22314, or you can call 1-800-685-0105. That's between 9 and 4 Eastern Time. Now remember, this is for doing Marsville at a single school. For a slight additional cost, you might wish to get involved with a regional Mars link-up or help set one up yourself. Last year, 29 sites hosted Marsville link-ups nationwide. Also, you can get the curriculum package Rescue on Mars by ordering. You can order a copy of this teleconference or just write to us for more information. You can also visit a Challenger Learning Center. We now have 13 operational sites in science centers, museums, and schools throughout the United States and Canada, and at least 4 more will be joining the network in 1993. We'll have all that information again if you missed it at the end of the program. And now we're going to get back to our questions and answers. Let's go to the phones. We have a caller. Go ahead, please tell us where you're from and who you'd like to ask a question of.
I'm from Titusville, Florida, and I'd like to know do you know if there's been any life form on Mars?
All right, and who would you like to ask that question of?
Jack General. I don't know his name.
That's all right. We've asked you to remember a lot of people's names here today. For General McDivitt, would you repeat your question, please?
Do you know if there's been any life form on Mars?
Is there any life on Mars? I don't believe that we know that today. There probably isn't any life the way we know it, and it's going to take some exploration. That's why we're having this meeting here. But I think it's highly unlikely that we would see anything that would look like an animal the way we know it here on Earth.
Okay, very good. Thank you for your question. We now have a question for Dr. Griffin from Bobby Baker here in our studio. Bobby, where are you? Bobby's up front. Bobby, could you tell us, first of all, where you're from?
I'm from Fairview Elementary.
Okay, Fairview Elementary here in Pittsburgh.
Yes.
And you'd like to ask a question of Dr. Griffin. Go ahead.
Whenever we have a civilization on Mars, will we have cars or spaceships, or the scientists have built something new?
Okay, that's a good question. Dr. Griffin, did you hear the question? Would you like us to repeat that?
Could you repeat the first part? I couldn't hear his words.
Certainly.
Whenever we have a civilization on Mars, will we have cars, spaceships, or the scientists have built something new?
Well, when we have a civilization on Mars, certainly we will have spaceships to go from one point on Mars to other points on Mars that are a long way away, because the atmosphere on Mars is so thin that we don't think airplanes are going to be a practical method of getting around. On the other hand, cars, which could be built using Martian materials and utilize fuels that we would draw from the Martian atmosphere, could be very practical ways to get around. And so I think you can look forward to seeing roads built on Mars just as they have been here.
Thank you, Dr. Griffin. We have another caller coming to us by phone. Could you go ahead, please, and tell us where you're from and who you'd like to ask a question of?
I'm from Gibsonia, Pennsylvania, and I have a question for Dr. Jemison.
Very good. Go ahead.
Yeah, when will the humans be able to travel to Mars?
I think we need you to repeat that one more time.
About when will humans be able to travel to Mars?
About when, at what time will humans be able to travel to Mars for Dr. Jemison?
One of the things that we're doing right now very actively at NASA and other places around the world is trying to figure out how do we go there and what kind of things do we have to get there. For instance, right now we could develop a propulsion system or the engines to get us there, but how long would it take us? We need to answer questions about how well people survive for long periods of time and how do you keep them healthy. Earlier on you heard that people have problems when they get up into space for long periods of time because their heart changes a little bit, they lose some muscle strength, they lose their bone mass, and that's okay if you're just going to stay in space, if you're going to stay in weightlessness for a year. But what about if you go to Mars and then all of a sudden you have to adapt to some more gravity, and the people have to be able to operate on their own because there's no one there to take care of them like it is when they land back here on Earth. So that's one of the things, the questions that we have to answer. We also have to answer questions as to how are we going to provide enough food and water and atmosphere. All those things you all are talking about for Marsville, we have to answer before we can send people to Mars for a long period of time or just to make the trip at all. When will people go? Let's hope that it's sometime close to after the turn of the century, because I'd love to go too. And if we wait too much longer, I'll be too old.
I don't think that's too likely, Dr. Jemison. Don't go away. We have another question for you from Dominique Fisher here in our audience. Dominique, where are you? Let me come over to you. Dominique, where are you from?
I'm from Prospect Middle School.
Here in Pittsburgh, and you have a question for Dr. Jemison.
I would like to know, were you scared the first time that you went up in space?
Well, my first trip up in space was just about a month ago, and I wasn't afraid. In fact, I was very, very happy. I was sitting on the middeck of the shuttle, and there are not a lot of windows in the middeck, so I couldn't see out, and there are lots of lockers around, but the other two astronauts that were there, Dr. Jan Davis and Dr. Mamoru Mori, we all three of us had the biggest smiles on our face because we were so excited about finally going into space. It was the first time for all of us. I think any time you take a big adventure like going into space, you have to be aware of possibilities, of danger. That way you can plan and make sure things work out right. You study enough so that you can understand the problem, and then you do the things so that you can help prevent any problems, and then you try to come up with ideas as to what to do just in case you have problems. So in that sense, I was very aware of what was happening and felt very comfortable, and I'll be extremely happy to do it again.
Dr. Jemison, we've been focusing a lot this afternoon on exploration, and I think the audience might be interested in hearing from you, if you don't mind, some of the things that you did before you went into space, because I know you were with the Peace Corps in Africa and you did some things that helped prepare you for that great adventure you took.
I really believe that just about everything you do in life prepares you for your next step. One of the things I did was to work in West Africa, and it's a place that doesn't necessarily have very high technology kind of medicine. In fact, I did a lot of things where I had to work with equipment that's not very advanced and just a few little things. In fact, one time when I was in medical school, I worked in a refugee camp in Thailand, and the hospital had gravel floors. But I learned about observation. I learned how to take care of people with very little supplies. And all of that's very helpful when you talk about going into space. For instance, you won't be able to take your own CAT scanner with you, which is a huge piece of equipment to take care of people medically. You're not going to be able to take up every drug that you ever thought of, so you have to figure out exactly what do I need. So working in West Africa, where I had to take care of patients with little equipment, was very important to helping to learn how to get prepared for a trip where you're going to have to be on your own again.
Dr. Jemison, thanks very much for explaining all that to us. We have another caller. Would you go ahead, please, and tell us where you're from and who you'd like to talk to?
I'm from Calvin Williams in Tucson, Arizona. I have a question about where is the money going to come to build the spaceship to go to Mars?
Where is the money going to come from to build a spaceship that goes to Mars? Do we want to, why don't we direct that to Dr. Griffin down in Washington. Dr. Griffin, can you tell us about some budgetary matters here?
Where are we going to get the money? Well, that's the question everyone asks about everything in government. I think the best way to answer the question, though, is to indicate how little we really spend on space. NASA spends every year an average of about $14 billion in round numbers, and that sounds like a lot, and it is, but it works out to something on the order of $10 for every taxpayer in the country. And if you think about it, we have many activities where we waste a lot more than $10, often in a day, and certainly in a few days. Many of us have habits where we spend more than $10 in a very wasteful or leisurely fashion. So I think if you look at what we spend on space versus what we spend on other things, it's not hard to talk ourselves into saying that a trip to Mars, a voyage to Mars, would be worth an extra dollar from a taxpayer.
So it's a small fraction of the federal budget, but it's a great investment in our future. We have another caller out there. Go ahead, please.
Hello?
Yes.
This is Susan Anderson from Tempe, Arizona.
And you'd like to ask a question of whom?
I'm from General McDivitt.
Very good. Go ahead, please.
Why is it that you're 2 inches taller when you return from space travel? I've heard about this.
Yes, please repeat
Would you repeat that, please?
I'm sorry. I heard that when you return from space travel, you are 2 inches taller than your normal height.
Yes. Change in size when you come back.
Right. Why are you taller after you get back from space than you were before you went? Well, when you're standing up on the Earth for a long period of time, the weight of your body is moving down towards the ground, and so you're shortening up your spine, whether you want to or not. As a matter of fact, that happens when you get older, too. I'm 63 now, and I'm about 1.5 inches shorter than I was when I was 18, so it's an age problem. Maybe I should go back in space. But anyway, when you're in space, you don't have the force of gravity shortening you up like that, and you tend to stretch out. So when you come back to Earth, you're just a little bit taller than you were when you left. Unfortunately, though, after you're on Earth for a little while, you get right back to the same size that you were before.
General, there are some other things that happen to your body in space that are reversible when you come back?
That are not reversible?
That are reversible.
That are reversible. Well, Mae Jemison talked about it a little bit. When you get back to space, your heart gets deconditioned. Just walking around here on Earth takes a lot of effort. So as you move around, your heart has to keep pumping real hard. Up in space, when you're floating around, it takes practically no effort. So your heart, like any other muscle, just gets tired. And when you get back down to Earth, it takes a couple days for it to rehabilitate itself, get back into shape.
All right, General, thank you. We have another question from the audience for Dr. Jemison. Michael Schau. Michael, are you here? Right in front of me. Boy, was I well positioned. Michael, did I pronounce your name correctly?
It's true.
Thank you. And could you tell us where you're from?
I'm from Fairview Elementary at Fox Chapel.
Very good. And you have a question for Dr. Jemison.
Yeah. If you stayed in Marsville for more than a year, when you came back to Earth, could you survive the greater gravity?
That's a good question. Is Dr. Jemison still there?
I'm still here, and
Yes.
I heard the question. If you stayed in Marsville for more than a year, would you have any problems coming back to Earth? And I guess the question is, if you stay at 1/3 gravity, Earth's gravity, and you come back to full gravity field, what happens? Well, we know right now that the Russian astronauts stay up in space for a year where we presumably have 0 G, and they're able to come back and eventually adapt. But they do some very interesting things with them. They end up exercising a lot every day. And they also end up coming back to Earth and going into a specific rehabilitation program to get their heart back up into activities and get their muscles strong again. So yes, I think that people will have the ability to survive once they get back on Earth, but we have to figure out what to do so that they'll come back and they'll adjust to the gravity here.
Thank you, Dr. Jemison. Thank you, Michael, for your question. We have one last question. Time for a short one. We can go to the phones. Is the caller there?
Yes, I'm here. I'm Scott Becker from Seminole Middle School in Plantation, and I'd like to ask a question to General McGriffith.
General McDivitt, yes, go ahead.
Can you build underground in Mars, and if you can, what's involved?
Can you build underground on Mars?
Right. I think you can build underground almost anywhere. You just have to bring the right tools. The thing that we're going to have to do in Mars is to get underground, probably, to do some thermal protection. As you heard earlier in the program, it gets very cold on Mars, and the dirt will probably be a good insulator. So getting down in the ground is going to be important, and I'm sure that we'll be able to do it.
Okay. And what kinds of soils will they have up there, General, will they have to contend with? Will it be similar to the lunar surface?
I would think it's going to be similar to the lunar surface, where we had a little layer of dust, and then we had some very large boulders and some very rocky parts, some lava flow. But I think it'll be just sort of like Earth. You know, it's different every place you go. So I think when we get to Mars, we're going to have to make sure we get to the right spot.
Absolutely, and that is the thrill of exploration. You know, that just about completes our program. I'd like to take a moment to thank each of our guests who took time to share their experience with us today. Dr. Mae Jemison out in Chicago, Dr. Michael Griffin down in Washington, and General James McDivitt here in our studios. And a special thanks to our team of 5th and 8th graders from Boyce and Fort Couch Middle Schools here in Pittsburgh. In addition, we wish to extend our thanks to Rockwell International, to the Telephone Pioneers of America, and to all the members of the Challenger Network who helped make this program possible. And so for Challenger Center for Space Science Education, I'm Dave Zarin, thanking you for joining us today and reminding you all to reach for the stars. Bye-bye.
Corporate funding for this program was provided by Rockwell International Corporation.